Okay, let's do a deep dive into something that, well, sounds like it should be really simple. How high are we? Specifically, how high is our sun sitting above the middle of Milky Way's disk?
Right.
You'd think, with all the tech we have, we'd have that number totally nailed down by now.
And that's exactly the puzzle, isn't it? Because as the paper we're looking at shows, and it covers like a century of trying to answer this getting that height, it hasn't been simple at all.
A century. Wow.
Yeah, and the kicker is the newest data, the really precise stuff from Gaia. It's actually, in some ways, made things more complex, not less.
Huh. Okay, so our mission today is to unpack that. Why has this, seemingly basic measurement been so tricky?
Exactly. We'll look at how the estimates have changed over time.
And see how this new data complicates things.
Right, and why it reveals just how dynamic and messy our galactic neighborhood actually is.
It's not just a number, then. It tells us about the galaxy itself.
Precisely, our place within it.
So why is it so important? Why do astronomers really care about this specific height, this Z?
Well, it's pretty fundamental for galactic astronomy. Knowing our height, our offset from the plane, it's crucial if you want to interpret observations correctly.
How so?
Think about it if you're counting stars in a patch of sky or mapping out dust clouds. If you don't know whether you're looking slightly up or down or straight along the middle.
Your counts are going to be off, like measuring furniture on a sloping floor, you said.
Exactly that kind of idea. And it directly ties into the standard map astronomers use, the galactic coordinate system, the zero latitude plane for that system.
The one from 1958.
Yeah, that one. It was defined to pass right through the sun.
Convenient for us, I guess.
Super convenient. But if the sun isn't actually in the true physical midplane of the galaxy?
Then our whole map is slightly tilted relative to reality.
Basically, yes. And that ripples out. It affects how we pinpoint the galaxy's true center, dynamically speaking, and, whether the supermassive black hole SGRA sits perfectly in that plane from our perspective.
Right. Didn't you mention some recent work tying this offset to SGRA?
Yes. Some of the studies suggesting a smaller offset found that placing the sun at that height actually puts SGRA right where you'd expect it to be in their defined midplane, which is, well, neat.
And it even matters for us here in the solar system. Habitability.
Surprisingly, yes, our vertical position affects the cosmic radiation we encounter, and the sun naturally bobs up and down as it orbits the galaxy.
So our height influences where we are in that bobbing cycle.
And whether that cycle takes us through potentially denser, maybe more hazardous regions like spiral arms more or less frequently.
Okay, so it's not just academic. It links galactic structure to, well, our local environment.
Definitely. Big picture and small picture.
Given all that, you really would expect it to be settled. But you said the history is messy, like even 100 years ago?
Oh, yeah. Harlow Shapley, way back in 1918, he already figured the sun was some 20 parsecs north of the plane.
20 parsecs north. Okay, so not in the plane, even then.
Nope. But since then, get this, the estimates have just bounced all over the place. The paper lists dozens.
Like how much variation?
Huge. You see some studies, say, in the 50s and 60s, using hydrogen gas or certain types of stars, getting values as low as like 4 or 5 parsecs.
So barely above the plane at all, almost sitting right on it.
Pretty much. But then you look at other studies from around the same eras, maybe using Cepheid variable stars or just general star counts.
And they got higher values.
Much higher, like 35 parsecs, even one around 42 parsecs.
42? That's a massive difference from 5.
It's enormous, and it's not just old data. Even using the same modern-ish data from the Hipparcos satellite in the early 2000s, different analyses came up with answers ranging from about 5 parsecs all the way up to nearly 35.
Just based on how they crunched the numbers.
Essentially, yes. Different assumptions, different ways of defining the plane using those stars. It really shows the difficulty wasn't just about having fuzzy data.
So was there ever a kind of consensus value?
Well, the paper mentions that if you took the median of about 55 previous estimates, it kind of settled around 17 parsecs, give or take 2.
Okay, 17, so moderately north.
Yeah.
A sort of compromised number.
You could say that. But those really low and really high estimates never fully went away. They kept popping up.
And what made it so hard historically? You mentioned data fuzziness, but what else?
A lot of it was the galaxy itself. I mean, the disk isn't a perfect frisbee, right? It's warped at the edges.
Like a bent record.
Kind of, yeah. And there are local structures near us, like the Gould Belt, this tilted ring of young stars that could really bias your sample if you weren't careful.
Ah, so if you mostly measured stars in that tilted structure, you'd think the whole plane was tilted.
Potentially, yeah. And the big one, always, is dust. Interstellar dust blocks starlight, makes things look dimmer and farther away, or sometimes redder. It messes with distance measurements, which are key here.
Okay, so all these problems,
Yeah.
it leads to a basic question, doesn't it?
Mm.
How do you even define the middle of something that's warped and dusty and has local weird bits?
Exactly. That's the core issue. Your estimate of the sun's height completely depends on what you use to trace out that plane.
Tracers,
Right.
right? The objects you measure against.
Mm-hmm. And if you pick different tracers, you can get different answers.
What kinds of things do astronomers use as tracers?
All sorts. The paper lists neutral hydrogen gas, that was the basis for the old 1958 definition. Then there are young stars, star clusters, those dark clouds where stars are forming, glowing HII regions, older stars, remnants of supernova. Lots of options.
And using, say, young stars versus old stars might give you a different middle.
It seems increasingly likely, yes. Different populations might settle into slightly different average planes or respond differently to the galaxy's dynamics.
Okay, so fast forward a bit, but before the big Gaia data dump, was that 17 parsec median number still the kind of go-to value, or were people starting to question it?
Oh, it was definitely being questioned. Just before Gaia really hit its stride, there were some pretty significant studies, especially ones focusing on very young, massive objects that were finding much smaller heights.
Smaller, like back down near those really low historical estimates.
Exactly like that. For instance, Reed and colleagues in 2019 used masers, basically natural microwave lasers in star-forming regions.
Pinpointing young stars very precisely.
Extremely precisely, yeah. And they got a height of just 5.5 parsecs, plus or minus almost 6.
5.5. So consistent with being very close to the plane indeed. That's way off from 17.
It really is. And interestingly, they noted that this plane, defined by the young stuff, matched the old 1958 hydrogen gas plane pretty well. And putting the sun there helped align the position of SGRA within that plane.
Huh. Any other studies around that time finding low values?
Yep. Anderson and colleagues, also 2019, looked at HII regions, another classic tracer of young, massive star formation. They found, again, a very similar low value, 5.6 plus or minus about 2.6 parsecs.
Okay, so just before Gaia, you had multiple lines of evidence using young tracers pointing to maybe 5 or 6 parsecs, challenging that older 17 parsec consensus.
Right. And they suggested maybe the reason older studies using stars get higher values was because the stars right around us aren't symmetrically distributed. Maybe there's a local clump or asymmetry making it look like the stellar midplane is higher nearby than the true galactic midplane traced by younger things spread further out.
All right, that really sets the stage then. A century of back and forth, different tracers, different problems, and then this emerging picture of maybe much lower height. And then Gaia arrives.
The game changer. Or so everyone thought. Billions of stars, incredible precision on distances, motions.
Surely this had to nail it down, right?
Mm-hmm.
Finally.
You would absolutely think so. But as the paper puts it, Gaia actually, quote, compounded the question's complexity.
How does better data make a simple question more complicated? That feels backwards.
Because Gaia didn't just measure things better, it revealed the structure of the Milky Way's disk in mind-blowing detail. It showed it's not just a bit warped, it's dynamically alive.
Alive how?
It confirmed features we suspected, but it also found widespread, non-equilibrium dynamical features. Basically, the disk is waving.
Waving, you mean like ripples, like throwing a stone in a pond.
Sort of, yeah. Large-scale vertical oscillations moving through the disk. Think waves propagating up and down through the stars and gas.
Whoa.
So this means the whole idea of a single, simple, flat, static midplane. It's just too simple. The galaxy itself is more complex. The plane is moving, oscillating.
Which makes defining the plane, or our height relative to it, much harder if the plane itself isn't staying put.
Precisely. Which part of the wave do you measure against? Which tracers are caught up in the wave and which aren't? Gaia revealed the complexity was in the galaxy all along.
Okay, that makes more sense. So what did the actual result from Gaia start showing for the sun's height? Did they agree, at least?
Not really at first. Again, it depended on the method in which Gaia data release they used. There was an early dynamical analysis by Widmark using the first data release, DR1. Got 15.3 parsecs, plus or minus about 2.2, so kind of near that old median value.
Okay, maybe settling things.
But then using the next data release, DR2, with the same analysis method, the same researcher got 4.76 parsecs, plus or minus 2.3.
What? From 15 down to less than 5? Just with better data using the same technique?
Yep. Shows how sensitive these things can be to data improvements or perhaps subtle changes in the sample.
So Gaia DR2 results were pointing low again.
Well, that analysis was. But another analysis of DR2 data by Bennett and Bovey, using a different dynamical approach that actually tried to model those vertical waves.
Say, accounting for the waving.
Exactly. They found a value of 20.8 parsecs plus or minus only zero point 0.3. Very precise.
21, so now we're back up higher than the old median, with high precision.
Right. So with Gaia DR2, you had one analysis pointing near 5, another pointing near 21. Still no simple answer.
This is kind of amazing. More data, still a huge range. What about even more recent data, like EDR3?
People kept digging, of course. Smart and colleagues used EDR3, focusing on stars near the sun, and they found something really fascinating.
What now?
The height they measured seemed to depend on the age of the stars they looked at.
Seriously? How?
They found values around 4 parsecs if they used young stars.
Okay, consistent with those other young tracer results.
But it climbed up to maybe 15 parsecs or so if they used older stellar populations.
So it really looks like different components of the disk, young stars, older stars, gas might actually define slightly different midplanes or sit at different average heights.
That seems to be the emerging picture. Gaia's precision isn't giving us one clean number, it's showing us the messy, layered, dynamic reality of the galactic disk. Different parts behave differently.
Okay, so let's try and sum this up. Where do we actually stand today on this question? How high is the sun above the galactic midplane?
Well, we can say with very high confidence that the sun is north of the plane. That seems settled.
North. Got it. But the number?
The exact number, it still really depends. It depends on which population you use to define your plain gas, young stars, old stars. It depends on the analysis method you use, simple geometry, complex dynamics, and it seems it might even depend on the specific age range within the stars you pick.
And the reason for all this uncertainty, even with amazing data like Gaia's, isn't the data quality anymore?
No, not primarily. It's the underlying complexity of the Milky Way itself. The disk isn't the simple, flat, static thing we might have once imagined. It's warped, it flares out, it's got these dynamic waves running through it.
Gaia just showed us that complexity in undeniable detail.
Exactly. Better data revealed a more complicated reality.
So we've gone on quite a journey here, a century of trying to pin down this one number, seeing estimates swing from maybe 5 parsecs up to over 40.
Settling for a while around 17.
The newer pre-Gaia results pulling it back down towards 5.
Only for Gaia to arrive, and while giving incredible precision, reveal the disk is waving and dynamic, leading to results that still range from around 4 or 5 up to over 20 parsecs, depending on how you slice it. Wow.
And you know, all of this really forces us to ask a more fundamental question, doesn't it?
Which is?
Given everything we now know that the disk isn't simple, it isn't static, and different tracers seem to give different answers, do we need to rethink how we even define the midplane?
Like, is there even one single midplane to measure from?
Maybe not in the simple way we thought. How should astronomers agree on a standard map, a standard reference frame for our galaxy, when the structure itself is so complex, so dynamic, and maybe even looks different depending on what population you're focusing on?
That's a really deep question. It's not just about finding a number anymore. It's about how we fundamentally map and understand a living, breathing, waving galaxy.
Precisely. Gaia's precision didn't just refine the old picture. It showed us we might need a new frame for the picture entirely. Sometimes more data reveals the universe is just wonderfully more complicated than we assumed.